Welcome back. We're now going to walk through a more complete example of matrix factorization and hope to expose its utility a little bit more. We're going to start with text data. Now, you may not have seen text data so far, so I'm going to start with a complete treatment. Here, I have 4 documents. Now, obviously, these are short documents. Perhaps they're social media updates or comments. The first, it's about my cat, likes to eat dog food, won't eat tuna, but loves dog food. Second document, check out this video of my dog chasing my cat around the house. He never gets tired. Cat's not a dog toy. The third document, I injured my ankle playing football yesterday, bruised and swollen. The fourth, so tired of being injured. My ankle just won't get better. Sprained it 2 months ago. You ought to be able to see from looking at these 4 very short, simple documents that there are some themes going on here. And our goal will be to uncover those themes automatically. Now, again, this is still a very small example that fits on a slide. This is not a case where we would actually use this technique, but I hope that you can see that in the real world, we will have many, many more documents to work with. Now, you'll notice that some of the words are highlighted in red. The reason is that those are the only words that appear in more than one document. We first, in text mining, remove all of the common words. So things like the, is, a, he, will all be removed. We call those stop words, and they're generally removed when the data is first read in, because they don't help us, they don't have any semantic meaning behind them. After the stop words are removed, we focus on the words, as I said, that appear in more than one document, because if they only appear in one document, they're not going to help us draw connections between documents. Now, the way that this data gets transformed into numeric data that the computer can use is through a term document matrix. So here along the rows, I have all of those terms that were highlighted in red: cat, dog, tired, injured, ankle, sprained. And along the columns, I have the 4 documents. Each entry in this matrix tells us how frequently or how many times the word on that row appeared in the document on that column. So for instance, the word dog appears 3 times in document 2, as can be seen by the 3 in the 2-2 position of the matrix. So in this example, our observations are the documents, and the words are the variables that describe those documents. Now, each of our observations begins as a point in 6-dimensional space, which means that it has 6 coordinates along some basis. Here, that basis is cat, dog, tired, injured, ankle, sprained. Okay, and so this coordinate representation tells us that in order to reach document 1 in space, I would go 1 unit along the direction of cat and 2 units along the direction of dog. Those terms form the basis of our 6-dimensional space, that elementary basis. And now what I'm going to do is approximate this matrix using a matrix factorization. And so the computer tells me that this matrix is approximately equal to these 2 matrices multiplied together. Now, you'll notice that I have chosen 2 latent factors here. The number 2 was an input to the computer during this process. So I told the computer I want the best rank 2 approximation for this data. Okay, so I had to tell it how many factors I wanted. And this is an approximation Because if I actually multiply those two factors together, I don't get my original matrix perfectly. But what I get is pretty close. It's really not bad at all. And I want it to be completely clear that how I got this is not something we've talked about. Okay, so I just said, hey, computer, give me two matrices that factor this one, and it gave me these two. That's as much as you need to know about that right now. Talk about all those details later. And so now, just knowing what we know about matrix multiplication, each column of the result here, the result being B, what I started with, can be written as a linear combination of these factors. And these linear combinations are the new coordinate representations of the data. So for instance, the second column of B can be written as the linear combination 1.7 times factor 1 plus 0.1 times factor 2. And we might use that to conclude, well, you know, it seems like document 2 has more to do with factor 1 than it does with factor 2. Just because the coordinate along factor 1 is much bigger. Well, that's great. How do we interpret factor 1? Well, for that, we have to go back to our original basis and realize that factor 1 can be expanded in the original basis. And so it has non-zero coordinates only for the directions cat, dog, and tired. A logical way to kind of label that collection of words might be pets. And similarly with factor 2, when we look at the loadings in factor 2, again, that's just the entries in these columns, we would see the large values around injured ankle and sprained and might call that injuries. So this first matrix allows us to see those latent topics that we uncovered, which were pets and injuries. The second matrix gives us the scores or the coordinates, and they allow us to describe the observations, the documents, according to the new factors. So for document 1, it seems very clearly about factor 1. Document 2 is really mostly about factor 1, mostly about pets. And documents 3 and 4 are also very clearly about the second factor, which was injuries. And so we were able to pull out all that information about our documents just from this matrix factorization. And so I hope it's clear that the reason why we want this new basis is first because I want to use some subset of those new basis vectors to reduce the dimensionality of the data while keeping the patterns intact. Now, the way that this reduces the dimensionality of the data is that originally I had 6 variables, 6 terms in which I represented the data. And so I had coordinates for each observation along those 6 terms. And by the time I was done, I only had 2 coordinates for each observation, representing each of those latent factors. And the hope is always that those new features, since they are linear combinations of the old ones, will have some interpretation. Now, I've bold and italicized hope because this does not always happen, but we hope it does. Generally speaking, the interpretation of those new basis vectors, those latent factors, is subjective. But we just look at the loadings to find the variables that have the highest loading values in absolute value and try to interpret their collective meaning. Let's have a little bit more practice with this. Let's suppose our original variables were height, weight, head circumference, verbal score, and quantitative score. Both of those scores coming from some aptitude test. Then household income and house value. And let's see if we can assign some new meaning to these new basis vectors that I'm about to show you. The first, axis 1, makes our life a little easy because there are zeros for the last 4 variables. And so I just have to come up with, what is it about height, weight, and head circumference that is, all related. So you might call that size. The second axis has zeros for the first 3 variables and non-zeros thereafter. However, it's clear that the largest numbers combine verbal score and quantitative score. So perhaps you might say ability or aptitude or test-taking ability. And then the final axis combines household income and house value. And perhaps we might call that affluence. We'll get a lot more practice with this in the weeks to come. The major ideas that we've talked about this week are linear combinations, linear dependence and independence, which motivated our discussion of vector span, which motivated our definition of subspace and the dimension of the subspace, hyperplanes, basis, vectors, coordinates. We even ran a generic factor analysis. We'll do a lot more of that, as I said. And these very important terms at the bottom, loadings and scores or coordinates. Thanks. I'll see you again soon.